My name is Pedro.
And I'm Nikita. I'm a product marketing manager on cybersecurity at Google, and I do marketing for security products.
And I'm just a security engineer on the Google open source security team, where I actually work full-time making security contributions to important open source projects. In our work explaining the new cyber threats to customers or repository maintainers, we've often found analogies to be very useful tools, which is why we'll actually start today with COVID-19, since it's something we all unfortunately experienced and remember vividly. For example, you probably remember images like these. In 2020, we all saw many graphs like the one on the left, showing the exponential growth of a contagious virus, how one case could spread to 2, 4, 8, 16, and so on, eventually making its way around the world. We also saw images like on the right, of worldwide travel patterns and how COVID would spread through social networks. We honestly witnessed firsthand just how connected the world has become. And with that in mind, here are 2 more graphs. Again, a striking exponential increase starting at the end of 2019 to 2020, and a highly interconnected network. But these 2, as you might expect, aren't actually about the spread of COVID. They're about open source projects and software supply chain security. The graph on the left actually shows the rise in software supply chain attacks over the past few years. These are hacks that target a piece of software or some component early in their own software development lifecycle in order to harm a different target later. The enormous 480% average growth rate over the 4 years shows just how lucrative and enticing these attacks have become. And on the right is an image from the deps.dev website, which we'll mention quite a bit today. It shows a typical open source project right there, together with the other packages that it depends on in order to function. As we're all aware, open source software is incredibly interconnected. And while these connections and code sharing speed up development and support innovation, they also mean that security risks or vulnerabilities in one project can impact many others. Just as COVID's spread was a direct result of how people interact and depend on one another, today we'll explore how vulnerabilities can spread based on how projects interact and depend on one another.
So here's our agenda for today. We'll start with a quick overview of what is open source software. Then we'll talk about how supply chain attacks are affecting open source projects. Then Pedro will dive into the topic of dependencies and how the web of connections between open source can cause risks to propagate. And that is the last point, is why we'll be using public health efforts during COVID as a familiar analogy. We'll borrow from lessons learned during public health efforts to take steps to protect ourselves and others. By making this analogy, we don't intend to downplay the severity of a global pandemic that so severely affected millions of people. We're using COVID and public health efforts to respond to it as a way to make the unfamiliar more familiar, and we hope that it will be a useful frame of reference. Any comparisons we make are meant in the most respectful way. So first off, what is open source software? We're talking about projects whose code is made freely available for anyone to use, modify, and build upon. You might think immediately of big name projects like Linux, Android, and Chrome shown over there. These projects have giant communities built around them of hundreds of contributors. But there are so many smaller open source projects as well. Maybe a project you start to try something new, or just because you care about a particular feature. And even though these projects may stay small, they can become crucial parts of the overall ecosystem of shared software. So open source is everywhere, including in essential infrastructure. So this slide shows data from a survey of different industries, outlining how many of their code bases used open source code. Turns out, almost all of them do. 96% of enterprise software, 93% 90% of healthcare, 97% of financial, and almost 100% of the surveyed energy industry code bases contained open source code. This presence in essential infrastructure means that protecting open source software is actually a national security concern. In fact, in 2021, the US government issued an executive order on cybersecurity that included provisions about open source. And in 2022, bipartisan senators crafted a bill to protect open source software. But if you're a more visually oriented person than a legislatively minded one, here's a different way of understanding this emphasis on securing open source. You may have seen this before. It's the classic XKCD comic for this topic, emphasizing how open source is foundational to all digital infrastructure. But it also highlights how important people are in this equation. If you're that developer in Nebraska, thanklessly maintaining a small yet essential project, you might not even know that it's so vulnerable, that it may have become an attractive target. You might not be getting the support you need. And when it comes to open source, security has a lot to do with the people behind these projects, the actions they take, and the ways those actions can affect others. In fact, we'll hardly talk about code at all today, and our main points apply no matter which coding language or platform you use. So now let's talk about supply chain attacks. There's an official definition at the top here that you can see, but for today's purpose, we can just say that a supply chain attack involves injecting code into your project to harm those who depend on you. And while this definition is about attacks, not everything we'll talk about today starts from a malicious mindset. Some things just start as innocent bugs that nobody had noticed. For example, one of the most recent supply chain emergencies that dominated the news started as an innocent bug that had been overlooked for nearly a decade. When it was finally discovered, it set the internet on fire. A vulnerability in Log4j, an open source project relied upon by a huge portion of the Java ecosystem, sent developers around the world scrambling to patch an accidental bug that opened a major security risk across the entire ecosystem. Or there was leftpad, which wasn't an attack per se, but just a few lines of code that disappeared and broke the internet. Or any of these other headlines, from banking to business. It seems like most hacks we hear about these days are related to supply chains. And open source is a major target, precisely because of its role in holding up the entire digital infrastructure. We might think open source projects are, well, open. Anyone can inspect the code for problems, right? In fact, there's a saying about the benefit of open source, that many eyes make all bugs shallow, implying that open source is in fact safer than other software, since so many people are looking at and reviewing the code. And that may be true for big projects, where there's a strong community and hundreds of contributors, plenty of support, and plenty of eyes. But for each of those big projects, there's at least as many smaller ones with maybe just one maintainer. Many eyes won't make bugs shallow if no one's looking, when it's just you taking care of a project that everyone uses, but that isn't getting the support it deserves.
And that was the case in this example that you might have heard of before, the event stream attack. Just take a look. In this case, a malicious actor asked, literally just asked, for ownership of a project, and the original maintainer gave it to him for the reasons explained here. And why did the attacker want ownership of this project? Well, as it happens, it was used by a crypto wallet app. So, after gaining ownership of the project, the new maintainer just added a little bit of code in order to steal crypto specifically Bitcoin, from the crypto apps users. This addition wasn't discovered for months after the package had already been downloaded 8 million times. And at this point, applications all over the web were already running the malicious code. And one thing that I find really striking about this example is just the simplicity of this attack, right? Especially compared to its enormous impact. While you may have heard of some very well-known supply chain attacks such as CodeCov or SolarWinds, which are super complex and maybe even have like nation-state level backing, others are really, really simple, just using social engineering like this to gain access to a project. So your project might not be directly involved with anything sensitive or critical, or, well, so you think. You never really know what your dependents are going to be doing. But it could still be at risk merely based on what it's connected to. For example, EventStream here was also used by many other projects. They may also have been affected even if they weren't the primary target, even if they were just collateral damage. But okay, we've already covered quite a bit. Let's switch gears here, because at this point you might still be wondering, what does this have to do with public health? Why did we even mention COVID at the start? Well, in our different roles, both Nikita and I work to raise awareness of supply chain security. And that requires communicating effectively about risk. So we researched papers about risk, and given the circumstances at the time, basically all their titles were some variation of lessons learned from COVID-19. In fact, there were so many, there was even lessons learned from the lessons learned from COVID-19, which summarized the hundreds of different papers into a few main lessons. And since the COVID pandemic and this sharp rise in supply chain attacks were happening at roughly the same time, I wondered whether there were any lessons from COVID for open source that we could borrow. And as it turned out, there were quite a few, but today we're going to focus on 3: evaluating risk, monitoring, and communication. But for these connections to make the most sense, we'll first need to talk briefly about dependencies, just to make sure we're all on the same page. And just a quick shout out to Nikki Ringland, Josie Anugera, and Eve Martin-Jones on the Deps.dev team for sharing some of the images and data on the following slides. So let's talk about dependencies, just to get everyone on the same page. These are packages that you add to your project to provide some sort of functionality, right? That's running pip install numpy on Python, npm react for JavaScript, go get Jain for Go, etc. So the projects that you rely on are your dependencies, and projects that rely on you are your dependents, also known as reverse dependencies. When you release your project as a package that others can install, all your dependencies also go along for the ride. Or to put it more visually, let's just take a look at how dependencies fit into a project's typical development process. Typically, a project starts with an idea. You think, I'm going to create a new tool, it's going to be great, it's going to be awesome with so many features, so you spin up a new repository and you start writing your code. But eventually, your project might actually start to contain other people's code too. And when I say that, you might immediately think of external contributors. These are people who get interested in your project or want to contribute a feature or fix some bug, so they open a pull request with their own code for you to accept. And that's a fantastic way to scale up a project and start creating a community around it. But there's actually another type of other code, shall we say, that we maybe don't think about as much, especially not in this way, and that's obviously dependencies. Somewhere along the line, honestly, likely immediately after you even started the project, you probably added a dependency on some other package. And let's be real, you didn't add one dependency, you added many dependencies, because dependencies are great. With just a line or two of code, you can build off of someone else's work and save yourself from having to write that functionality yourself. Honestly, in many ways, it's like having the world's greatest developers on your team contributing to your project. But there are 2 things to keep in mind about dependencies. First, when a bug is in your code, when it's in your repository, you can just fix it yourself. Even if it originally came from an external contributor, the code is in your repository. You can just go ahead and fix it. But when the bug is in a dependency, other people must be involved for it to be fixed. Even if you go ahead and you fix the bug and you send it in as a PR, someone else still needs to merge that PR. Someone else still needs to cut a new release version before you can actually benefit from it in your own project. And second, each dependency likely has its own dependencies. And each of them have their own dependencies. It can be turtles all the way down. So every dependency that you add increases the chance of there being a bug somewhere. And it's not a linear increase. It's more of an exponential one. So when you package up your code and you release it to the world, all of your dependencies go along with you. And when someone installs your package and adds it into their project, they're not only depending on you, but they're depending on all your dependencies as well. And let's be clear, like that's a good thing, right? That's how ecosystems of shared open source code get built. That's what supports so much innovation in open source. But it does mean that you might wake up one day and find out that one of your dependencies has turned into a massive security risk and set the internet on fire. And at this point, that affects not just your project, but potentially everyone else who depends on it. So, for example, say your project is the creatively named package A. And you added several dependencies for some functionality because, again, dependencies are awesome. And yeah, those dependencies have their own dependencies, and those dependencies have their own dependencies, and that's fine. Like, it works great. It's fantastic. But then one day, you might wake up and discover that there's a problem deep in your dependency tree, all the way down in package K over there. We can call this log for K. Well, that might actually have consequences for your project, because the problem might not be isolated to package K. It might affect package I, and it might spread to anything that depends on I. And at the end of the day, it might affect you, and all because of a risky project you might never have even heard of, because it's what we call an indirect dependency. And this isn't some theoretical problem. The vulnerability in log4j that set the internet on fire, that was one bug in one project that ended up affecting at least 17,000 projects connected to it either directly or indirectly. Indeed, as much as 98% of the time when a package is affected by a security vulnerability, it's affected indirectly, where the risk to you might not be so clear because you might not even be aware that you're affected by it. So you might be hearing this and thinking, okay, sure, I need to keep my dependencies up to date to make sure I have all the security patches. How hard can that be, right? Well, unfortunately, while it's easy to talk about dependencies with tiny little tree diagrams, dependencies often don't look like this. They look more like this, a complex, highly interconnected graph. So here you can see again a tiny little teal dot in the center, and that's our package, shall we say, and the lines point to all the other packages it depends on for some functionality. And these graphs, they might be bigger than you think. For example, the average NPM JavaScript package has around 6 direct dependencies, but 110 indirect dependencies. In graph form, that can look something like this, right? A typical project's direct dependencies, might seem interconnected, but still somewhat manageable. But then you compare that to its indirect dependencies. It gets a lot messier. And some projects bring more risk and more complexity than others. For example, there's this one, which has a dependency chain, 58 levels deep. But if you had added this package to your project, you might not even have realized the sheer number of dependencies that you're exposing yourself to. And you might not even be aware of the difficulty you'll have tracing a vulnerability through all of these different layers of connections. After all, installing this package is still just a matter of, shall we say, pip install XYZ, right? It's still just one line of code. So returning to the analogy of COVID, many of us had the experience of spending time with a friend only to get a phone call or a text a few days later when they'd found out that they'd been exposed shortly before meeting us. Heck, I had to make a few of those calls myself. So if doing contact tracing through just a few levels of connection were challenging, imagine tracking it through 58 such levels. I hope that this visualization of how open source projects are connected through dependencies is helping to show why so many lessons from the pandemic will be applicable to this topic. So for the rest of the talk, we're going to touch on lessons from public health efforts and apply them to open source software. We'll talk about actionable steps that you can take regardless of your experience with security.
All right, so lesson 1. Here's the first one. If we rewind to 3 years back, knowledge about risk was absolutely essential when COVID was at its peak. Without it, public health workers couldn't accurately judge risk, plan the right responses, or communicate guidelines to the public. Communication was especially difficult, and it was that some health organizations found emphasizing only the worst-case scenarios led people to make poorer decisions because they were overwhelmed. They could not communicate guidelines properly and plan the right responses. But you don't want to be understating risks either, right? So with time, health officials refined their guidance. They targeted different recommendations to different populations based on factors like age, immunity, workforce profiles with high-risk jobs, and so on and so forth, all based on understanding the different risks. So to connect that analogy to open source, how do you gauge risks to your projects and the projects around you so people make the right decisions? These are 2 free tools we can introduce you to that can help out a lot. Scorecard to understand your own or another project's risks, and then deps.dev to understand how projects are interconnected. With these 2 together, you can better understand what risk category your project falls into, how to evaluate projects you use or depend on, and which recommendations actually apply to you. So first off, the scorecard. The OpenSSF scorecard is a free automated tool created by the Open Source Security Foundation. It runs nearly 20 checks on open source projects. A check is a way to evaluate a common security practice known to correlate with risk. For example, one of the biggest indicators of risk is whether a project is maintained or not. You may be using a project or relying on it as a dependency, not knowing that it was abandoned years ago and is no longer getting bug fixes or any security updates, which you'd want to know about. This slide shows scorecards for 3 projects, and you can see how the different checks are weighted according to critical, high, medium, and low risks. Scorecard provides a ton of information for projects on GitHub and GitLab, with lots of ways to access it. Here are the 3 most useful ones for open source developers. You can use the Scorecard web viewer to look up scores for 1 million projects. The link for it is in the Scorecard repo on GitHub, toward the top of the README. If your project isn't included in the 1 million projects, you can run the CLI tool to get the scores. Again, instructions for those are also in the README. And if your project is on GitHub, you can add a GitHub action which will run scorecard on each change to your repository and alert you if any change you make causes any security regressions. Despite its name, scorecard isn't just scoring you. It's meant to help open source developers. It gives you advice on how to raise scores that indicate potential areas of improvement that makes scorecard super useful, not only to evaluate someone else's project, but also to understand the potential risks before you add it as a dependency. But it can also be used as a checklist of things to improve your own project's security. This slide exemplifies one of those pieces of remediation advice. It explains how a security policy helps people safely report vulnerabilities found in your project and suggests where you should place them or the files that and what you might say in it. The second tool that we talked about is Google's deps.dev website. That's the URL, deps.dev. We've mentioned deps.dev quite a few times by now. This site has a wealth of insights about millions of open source packages and how they're connected. So for instance, if you look up a package, you can see some information about it in the overview tab there. Often, you can see its scorecard score. And if you click on the dependencies tab, as this slide shows, you can see how many projects it relies on. You can click on the graph button on the right top corner to see a cool visualization like those we've shown in the previous slides. You can also choose that third tab to see the dependents, to know how many projects rely on this one. If it's your project, just that knowledge could shape how risk-averse or risk-tolerant you want to be. If that tab shows that it's a small toy project that many others are using, maybe you can worry less and have a greater risk tolerance. But if you find out that quite a lot of projects are relying on yours, that might guide you in future decisions and lower your risk tolerance.
And now for lesson 2, monitoring was key for containing COVID. But it was really challenging. Communities had to spin up entirely new programs like free testing clinics and contact tracing through telephone calls in order to try to limit the spread as it was happening. However, with time, we saw how advances like at-home tests made monitoring more accessible by bringing it directly to us. Likewise, new apps on phones warned us of possible exposures, and all that automation relieved some of the burden of making manual phone calls for contact tracing. All this monitoring made action plans possible. Some cities offered free home delivery of antiviral medication to high-risk individuals. Other places delivered food and care packages for those who tested positive in order to help contain the spread. By bringing those resources directly to people, they and the community around them were more likely to benefit from these resources than if people had to seek them out themselves. So for an open source project, the analogous solutions are tools for vulnerability monitoring and alerting, and dependency update tools. Monitoring tools like OSV, which stands for the Open Source Vulnerabilities Database, let you know whether you've been exposed to a vulnerability somewhere in your dependency graph. You may have heard of CVEs, the Common Vulnerability Exchange Program, but OSV is specific to open source and has a lot of associated tooling. And you can see all the ecosystems that it covers at the bottom of the slide there, and they're continuously adding new ones. OSV tooling can also alert you so you can take preventative action. Often, that action really is just updating to a new version of a dependency. So a project that you rely on discovers it has a vulnerability, it fixes that vulnerability, and then just releases a new version of their package with that patch, and all you have to do is update your package to use the new version. It's often painless, literally just a simple version bump. But if you have a large dependency graph, there could be a lot of updates happening all the time. And we're human, so sometimes we'll just forget or just get overwhelmed. So our suggestion is don't even try to remember. Just automate the process. Just as you'll receive a notification on your laptop or your phone letting you know about new versions of your apps or operating system, there are automated tools to send you notifications about your dependencies. They'll even send you pull requests, so all you have to do is merge them to update to a new version. And if you have automated CI testing, you'll even know right away whether there are any relevant breaking changes. You can think of these tools as delivering the needed resources right to your doorstep, making it easier for you to use them. On GitHub, there's Dependabot. There's also a RenovateBot that's available in basically all platforms, including GitHub. And many languages also have their own dedicated tooling for this.
All right, moving on to the last lesson. Analysis of successful community health efforts during COVID found that messaging and communication were key. Communities that were less receptive to outreach whether because of language barriers or distrust of the messenger, had worse health outcomes. What often helped overcome the messaging barrier was community members themselves. When trusted community members or leaders worked with health professionals to amplify their messaging, more people were receptive and able to adopt the recommendations. Speaking as a marketing specialist, this makes total sense to me. Effectively communicating can have a real impact. And we've seen from outreach efforts to improve security for open source projects that trust in the messenger makes a difference. So, help others. Yes, that often means code contributions. And certainly, if you have the ability to contribute improvements or bug fixes to projects, that can have an amazing impact. But communication can too. And I bet a lot of people in this room also have incredible skills outside of coding. You can raise the topic of security in forums where people respect and trust you, and communicate about why you think it's important to prioritize security improvements. Soft skills support community education. You can generate awareness by drawing on your own marketing skills, by publishing blog posts, articles, or even, as in my experience, raising awareness of the need for public sector support. I've seen from my own marketing work that these actions can help land open source security as a critical focus area in government forums and contribute to documentation. There's some growing evidence that projects that document their security are less likely to regress on them and more likely to maintain their hardened security over time. So we'll close with an example of this type of action. Remember how we mentioned security policies when talking about scorecards remediation advice? A security policy is a type of documentation for a project that helps people safely report a vulnerability and understand the project's security efforts as well. Well, this is an example of community outreach by Joyce Broom, a Google software engineer based in Brazil. She reached out to an open source project that's considered critical to digital infrastructure. A project like that little block in that XKCD diagram that we saw earlier. She suggested making the project's existing security policy even more visible to users by moving it to the standard location for GitHub projects. So someone looking to report a vulnerability could easily find it. This is a type of contribution anyone can make, regardless of tech ability. And the maintainer said yes. They thanked her, they made the change to boost the security policy's visibility, and then later they added this. This change got applied to 20 high-profile projects downstream. And downstream here is just another way of saying projects that depend on this one. So one non-coding action helped make at least 20 projects a little more secure.
And really, that's the final thought that we'd like to leave you with today. And that is that just as risks can propagate through communities, as we've shown, so can proactive, positive action. You can have an impact on those around you. So if you already maintain an open source project, please try out some of these suggestions. And if you're just new to open source, welcome. It really is a great place to be. So thank you everyone for listening, and we'd also like to give a special shout out to all the people who contributed to our talk. Any questions?
Any questions? Oh.
Not so much a question, but kind of a comment, or maybe you could elaborate on this. There's a phenomena here of software EOL, and I was listening to a web presentation a couple of days ago about web, not necessarily, this was with Python 3, Python 4 to Python 2 to Python 3.
Yeah.
Now, if you have something that's developed with an old Python version and you have a dependency that you really don't want to mess with to go to the next version, how does that affect this sort of thing? Because they were offering a little bit of, well, if we find a CVE in Python 3, we'll backport it to a certain version of Python 2 for you. And they also offered that we will also take a look at some of the dependencies in your project, but how would they go about maintaining a large database? Because I think they'd have to go through these sort of things going back from one version to the next.
Yeah. So just to make sure I understood the question, the question is regarding cases where it can be challenging to update to a new version. Also because, especially going from Python 2 to Python 3, there are many different things that would be needed to be changed in a project. Is that the question, basically? Yes. Okay. So in those cases, the suggestion here isn't necessarily like you must always be at head, you must always be at the latest version. That's not necessarily the case. In fact, you even see ecosystems such as Go, where by default, actually, you say, I accept any version above 1.2 or whatever, and it will just give you 1.2. It won't give you latest. It will give you the oldest version that satisfies your constraints, because that older version, it's the one that's been most tested. It's the one that people are most used to. And so, I mean, the suggestion here isn't necessarily like be at the latest version. It's be at a version that you trust, a version that you are confident in. One suggestion here would be that if you want to make sure that you're at a version that you can trust, is you can also pin your dependencies, right? So you can have a requirements file that has the hashes in them, and then you do pip install require hashes, for example, in Python. And that will make sure that you always get the version that you expect, that this old version of a package perhaps hasn't been modified so that you think that you're running the latest version that runs in Python, I don't know, 2.6, which is even end of life by now. But actually, it's someone put in a malicious version that is affected by it. So long as it's a version that you trust and that you are comfortable with, that is reasonably okay. It does mean that you need to do this monitoring in case there are any vulnerabilities that are discovered in that version that you are using. And if there are any, if you are very outdated, there may be significant breaking changes that you would need to deal with in order to bump to the next safe version. But that's honestly fine. It's a choice that the company needs to make, right? It's sometimes making these big migrations, especially from Python 2 to Python 3, or other big things with many breaking changes. A company can always decide, or a project can always decide to say, that is not worth it for us. We are willing to maintain this, to monitor this older dependency, and take, shall we say, the risk of eventually having to make this migration at a very short schedule because this old version is found to have some sort of vulnerability. That is okay. It's a choice that a company can make, right?
Any more questions?
All right. So thank you very much.
Okay. Thank you.